Welcome back. In the last few videos, we proved big theorems about bases, about the number of elements, about dimensions. What we'll do in the next few sections is look at one way of constructing a subspace and find a method to get a basis for it. All right, so in today's video, we'll be looking at spans and we want to figure out how to find a basis for a span. All right, so given a subspace W equals span of S with a set of generators S, find a basis B for W. So we are given a set of generators. However, a basis needs to be linearly independent, which S might not be. To find a basis B for W, we start with S and get rid of all elements that can be written as a linear combination of the preceding vectors. So the method depends on having picked an order for the elements of S, and the basis that you'll get depends on that order. So it's not going to be wrong, but if you switch the order of the vectors, the basis you'll get will be different. All right, let's try example 1.5.6. I'm going to look at the span of these three vectors inside E3. I want to find a basis B for W. All right, so I want to check whether this set is linearly dependent or not. So I'm going to put them in a matrix and I'm going to reduce it. This is what I got. So from this, we know that there are infinitely many solutions, and so we know that V1, V2, V3 is linearly dependent. In fact, we know more than this. If I had a line here, then I would have a line here, but the reduction would be the same. And so I have a solution. I have the coefficients to write V3 as a linear combination of the other ones. V3 is 3 halves V1 plus minus 3 halves V2. All right, so that tells us that V3 is redundant. V3 is redundant since I can write it as a linear combination. But I know more than this, so I don't need V3. I can get rid of V3. So span of V1, V2, that's the same as span of V1, V2, V3. That's something that we proved in theorem 1.4.2. All right, so now I'm down to two vectors. Do I know that these are linearly dependent? Well, yes. V1, V2 is linearly dependent. Because if I only started with V1, V2, if I'd only started with these two, I would end up with this. I would end up with only one unique solution, only the trivial solution, since I have a leading one in each column. And so the basis is V1, V2. All right, so I'm asked to write each vector in terms of B. Well, for V1, it's just going to be V1 plus 0 V2. For V2, it's going to be 0 V1 plus 1 V2. And for V3, that's going to be, we have it up here, 3 halves V1 minus 3 halves V2. In fact, you could read this in the third column of the reduction above. All right, so this yellow column here gives you the coefficients that you need. It gives you a recipe for V3 in terms of V1, V2. The way I think about it is the relationship between the columns doesn't change when you reduce. So if in the reduction here, the third column is 3 half times the first minus 3 half times the second, that's going to be true at the start as well. All right, so W has a basis with 2 elements, and so its dimension is 2. That tells us that W is a plane. In fact, it's the plane containing 0, 0, 0 and parallel to V1, V2.